Hello class, today we're going to talk about energy, and you did some terms on energy, and now we're going to talk about how to calculate energy changes. Remember, energy is, you can think of kinetic energy as temperature of how fast things are moving. So we're going to start with thermodynamics. Thermo means heat, dynamics is kind of like the study of. So basically thermodynamics is the study of energy. The first law of thermodynamics. There's three. We're going to deal with one this right now. The first law of thermodynamics is the energy of the universe is constant. So we've also said that matter is constant and cannot be created nor destroyed. Well, energy can change forms, but we have what we get. So energy cannot be created nor destroyed is what you can also say. So what that means is matter or energy cannot be created nor destroyed, but they can change. So when we burn a block of wood, the block of wood has lots of energy. The potential is there to give off energy. Then when you burn it, you change it to heat and light energy. So it's not going away. It doesn't disappear. It changes form. So this comes straight out of your book. It says the energy or the heat required to change the temperature of a substance depends on two things. The amount of substance being heated, which is the number of grams, and the temperature change. So you might want to write this in our notes, is the energy required to change something depends on two things, the amount and the temperature change. Putting this into perspective, if I take a small cube of ice, like just one simple little ice cube, and I'm just going to have that melt, versus if I take a huge meter by meter by meter chunk of ice, there's more ice there, which is going to take longer to change. And if I wanted to actually change that to be really fast, it's going to take more energy to do that. So how do we measure these energy changes? Calorie is the metric system unit of energy. So we measure in calorie. Now I know you guys have all heard of calorie dealing with your food calorie, like how many calories are in a Snickers bar, too many. But that's actually a food calorie is actually a kilocalorie, which is 1,000 calories to recall what kilo means. And that is why almost every label should have calories listed with a capital C, because it's a kilocalorie. But in chemistry class, we're not going to deal with calorie very often. We're going to deal with joules. So a joule is the unit of energy we will be using in chemistry. Some books use calories, some use joules. We're going to stick to joules and just go with it. So 1 calorie is 4.184 joules. We're going to be putting this on your note card. 1 calorie is equal to 4.184 J's, so there's your abbreviations you can put on your note cards. 1 cal is equal to 4.184 J's for joules. So a simple converting, how would I convert 60.1 calories into joules? We're always going to start with our given and just convert like you guys did the first unit. So start with your given 60.1 calories. I just gave you the conversion that 4.184 joules is 1 calorie. Calories cancel, so we're going to multiply those two numbers and get 251 joules. So we can go back and forth. So here's the new concepts today, is something called specific heat capacity. Specific heat capacity is designated by a capital C is the symbol, mostly probably from the capacity. Now I hope you guys understand that when you ride a bus it says the cap is like 63 or 72. Capacity is how many things it can hold. So a capacity is how much it can hold. So when you're thinking of specific heat capacity, we're going to deal with how much a substance can hold its heat. So here's the book definition. The amount of energy needed to raise the temperature of 1 gram of substance 1 degree Celsius. Amount of energy needed to raise the temperature of 1 gram of a substance 1 degree Celsius. And the specific heat capacity depends on the substance. Water is different than aluminum. Aluminum is different than copper. So it depends on whatever type it is, because each type of substance will hold different heat capacities. So the chart on page 70, if you have your book in front of you, you might want to turn to that one. I'll give it to you on the next slide, but we're going to come back to it. So the question is do metals have a relatively high or low specific heat capacity? If we look at the table, we'll be able to determine that. So hold on, because I have another question for you. So the question is you might just keep this in your head, you probably don't have to write this down yet, is do metals have a higher or low specific heat capacity? And the second question is, would it take longer to heat 1 gram of water 1 degree Celsius or 1 gram of gold? So you might want to abbreviate this and put this question down. Time to heat 1 gram of water versus 1 gram of gold. So the first question stated which one has higher, do metals have high or low? So if I look at these specific heat capacities, which comes from page 70, water has the highest on this list at 4.184. Does that number look familiar? And then we have ice and steam and a whole bunch of metals after that. So generally speaking, when we're comparing to water, metals have a low specific heat capacity. The next question is, would it take longer to heat up water or gold? Well, if we look at this, this is the heat capacity, how much heat it can handle. So it's going to store the heat. Picture this in a lake in Minnesota or a lake anywhere. Once the water's warm, it stays warm. In the summertime, the sun goes down, the water's still warm, so you still swim at night. Now that it's been cold at night, it's been cold for a while. That lake is pretty cold, so I probably wouldn't jump in. But in September, it was still not as cold at night. The lake was still warm, so you still jumped in. So because water has a high heat capacity, it holds the heat better. Whereas gold does not. Gold will actually transmit the heat and let it go in and out much easier. So it would not take very long to heat up gold, but it won't stay warm either. Where it might take a long time for water to heat up, but once it warms up, it stays warm. So here's an equation for you. So equation for calculating the heat or the energy for a reaction. Because we've had exothermic and endothermic reactions where one is warm, gives off heat, is exothermic. One is endothermic, which is it gets colder. We can actually now figure out how much energy those generate. When you put the zinc and hydrochloric acid, the solution got really warm. That was exothermic. We're going to figure out how we could actually measure that. So this is from your book. I'm not sure if you need to write it down, but we're going to talk about it. It's the energy or the heat required is Q is equal to the specific heat capacity times the mass in grams of sample times the change in temperature. So here is Ms. Rueckert's version that you might want to put in your note card. Q is equal to mc delta T. So Q is the energy or the heat required, M is mass, C is specific heat, and delta T is a change in temperature. So here I'm breaking it apart for you that Q is equal to the energy or the heat required. Okay? M is equal to the mass in grams. C is the specific heat. Just so you know this, that specific heat is, if you look at the unit, joules per gram degrees Celsius, because Q has to be in joules, mass has to be in grams, and our temperature is going to have to be in degrees Celsius. Delta means change. That's the Greek word for delta is change. So delta T is a change in temperature. which means you take the final temperature minus the initial. So if my room was 20 degrees to begin with and it went up to 25 degrees, the change in temperature is 5 degrees. So here's an example. Probably need to write this down so you get an idea of what we're doing here. We can at least write some of it down. So 1.6 grams of metal requires 5.8 joules of energy to change its temperature from 23 degrees Celsius to 41 degrees Celsius. Is the metal gold? So here's what we're going to write down. 1.6 grams, 5.8 joules from 23 degrees Celsius to 41 degrees Celsius. Is it gold? So we're going to write our equation down and substitute. Now you need to tell me what we have here. Do we have Q? Q is in joules, so that's 5.8 joules. M is in mass, so that's 1.6 grams. C is what we're after, and the change in temperature is going to look like this. So Q is 5.8 joules, mass is 1.6 grams, specific heat is what we're after, and our change in temperature is 41 minus 23 degrees Celsius. If I do the math here, where I have to subtract 41 minus 23 times 1.6 and divide both sides by that number, I'm going to get 0.2 joules per grams. I need to see Michelle. If I look on the table, the C value for gold is 0.13 joules per gram degrees Celsius, so it is not gold. These are the types of problems that we're going to be doing this unit. So hopefully you can follow that and we'll pick some more up in class. Have a good day.